Okay, third question of the midterm is about a motion study that we have to done. It says consider the block uh, on the slope as shown in the picture below. The slope angle with horizontal level is 30 degree. The block is 25 millimeter cube made with 304 stainless steel. At the bottom of the slope, there is a damper plate attached to a spring. Protect the block from impacting the end of the slope. The spring on a stretched length is 50 millimeter with the stiffness of K equal 1 Newton millimeter. There is no friction between the block and damper plate or between the damper plate and the slope. So there's no friction here. The only friction which is left is between the block and the slope itself. Coefficient of restitution between the block and damper plate is 0. So no impact between the block and the damper. The block will release from the rest position with 240 millimeter linear distance from the top steel plate with the stop plate at the end of the slope. So the distance between the block and the stop plate is 240 millimeter. Use the assembly file provided for this question. Note that the assembly is fully defined and you need to suppress or modify the necessary mate. The material are not assigned to the part, so you have to assign it. And it says simulate the motion analysis for 1.5 seconds at 500 frames per second with accuracy of 10 to the power of -4 and submit some plots that we need to do. So if I go and open the motion setup for this problem, yep, I build that. We'll wait if I, okay, so we have this motion setup, it's fully defined, and I need to, we have to define this motion. So we need to do a step-by-step bit based on what is given, and then we are going to define what we wanted. So first off, you see that this material is for the block 1. Let's define it from beginning. The model ring provided and the block and everything, and set 3 for stainless steel and is already defined, even though that the material is not defined, is actually defined. So the block material was all important, that is already given. So this paragraph is done. At the bottom is the bed plate. Okay, so the only thing that we have to define first is we have to define a spring between the damper plate and the end of the slope. So a spring K equal 1 with 50 millimeter stiffness on a stretch. So first we need to know what is this stopper plate is. It has to be 50 millimeters. So if you're going to the mate, and you will see that if you evaluate the mate that has been defined, one of them is distance, which essentially is a damper plate and the end stop, and you see that it's already at 50 millimeters. So you don't need to adjust it. It's good. But going back to motion study, we need to define a few things. First, let's change it from animation to motion analysis, and then we are going to define a spring. So I'm going to attach a spring here. It would be a linear spring between this plate and the end of that. It's K equal 1 and the honest stretch is 50 millimeters. So this is good. It doesn't have damper, and the rest of it is a study. Okay. So here you are. Maybe I have to define the motion parametric. So it would be 1.5 seconds. So it would be probably not here. It's 1 second. Maybe drag it to 1.5 seconds. Okay. And while I'm there, so this is how it defined for the total length of simulation. What else? After a spring, we have to define the friction that we need to have. And then while there are all we have here, it says friction, but I'm not sure that if coefficient of friction is given here. Well, it seems like there is no, essentially, it didn't say strictly how much is the friction, so maybe we do not define a friction at all. That's you don't need to define a friction because there's no mu is given for this problem. So we are going to simulate it without friction, and it would be based on the animation or whatever that we have here. But then we have to define our contacts that they have in order to do that. So the obvious contact that we need to define is between the block and these stopping end. So we're going to define a contact. Before that, let's define a gravity. This is obvious in a y direction, downward. And then we can define a contact, which the contact that we would like to define is between two solid bodies of the block and the stopper plate. It's not based on the material, and there is no friction defined for that. It's based on a restitution of coefficient, which is 0. That would define a contact here. What else is, before proceeding, let's evaluate the mates and see how many of these mates we have to keep and how many we have to suppress. So coincident one is between the slope and the block, which we are going to keep it. We are not defining friction, so we keep this one. The other coincident is between the side and this. We are keeping that. The limit distance is, so here is the limit distance that we need to define it. It says the block will release from rest region 240 millimeter linear distance from the stop plate and the end of the slope. So the block would have 240 millimeter from the stop plate. So if it is a 240, it means that the initial step from this should be 290. Initially, it's been defined as, if I double click, it says 140. So I have to put it at 290. 240 plus 50. 240. 240 is the initial step, the initial position. If I rebuild it, it should bring it all the way. Okay. So that's the initial distance that you have to define. So this limit distance is correct. Moving on. The other mate is with the stop plate. We're keeping that. This distance is not a limit distance. It means that we need to suppress this because we have to allow this stop plate go back and forth. So right click and suppress it. Coincident 7 is keep the stop plate there. It's okay and it doesn't have friction. We're not defining that. Coincident 8 is I feel like coincident 8 is duplicate of another coincident that we had, maybe coincident 4. Yeah, between 4, sounds like 4 and 8 is duplicate, so I will suppress it, coincident 8 as well. So now we check the mates, we add the gravity, we add the contact. What else is have to do that? Let's check it out. Assembly file provided, material already assigned. So simulation 1.5 seconds. Okay, 100. We have to go back to motion setting. We already defined the motion analysis 1.5, and here the FPS would be 500, and accuracy is 10 to the negative 4, which is 10 to the negative 4. By default, hit OK. And I think we should be all set. Even if it is not, we can analyze it and see how it's gonna go. So calculate that simulation. Okay, the block stop, moving, pressing against the stop plate. Stop plate is gonna bring it back up. Again, it's gonna push it back. And it's a stop at 1.5 second. Is that a 1.5 second? Yeah. Okay, so simulation seems being successful. Now we are going to define a few things here. Linear position of the block in the direction of the slope. So we are going to define a linear position of the block. So going this one back all the way to the beginning of the simulation, going to the plot. So essentially we would like to define it based on a displacement. It would be a linear displacement, and it would be between, I would select the endpoint of this versus this one. And we know that it should start from 240. What is the direction? It would be along this, which is gonna, if I select the block, the direction would be across the Z magnitude. So if I select, you see that it start from 240, maybe we have to reverse it in order to be a start from positive 240. So I'm going to go back to result, edit feature. So I select block and a slope. Maybe I will delete the block, first slope the slope, and then block. So let's reverse the order. And if I show the plot, yeah, you see it's gonna start from 240 and then working toward that. So that would be the displacement plot. Second is linear velocity of the block in the direction of that. Okay, so we know that that should start from 0, that velocity. So going to start displacement velocity, then linear velocity. That would be with reference to what points is that, is this point, or maybe velocity between this point and this point. Again, would be the part. Probably we have to first select the block based on what we learned, and then I'm sorry, first we have to select slope and then block. If I select the block, then it would be X direction. Yeah. Not sure if it is a start from -17 or it was a different one. Maybe maybe if I select the faces, would be different. No. I assume maybe that was a 0, but because of that it start, because that should be start from rest. Maybe if I right click here, going to giving the initial velocity, well, initial velocity is always 0, that it has here. Okay, moving on. How much does it take to how much is the block maximum velocity along the slope? So if I go back to linear velocity and show the plot, it shows that the maximum is 1344 to or you can export it and find the accurate number. And what is the final length of the spring? So in order to get the final length of the spring, the length of the spring is between the damper plate and this spot. So in order to do that, you have to get a linear displacement as a linear displacement between this point and this point. That would be the length of the spring. And if I select this point, it would be along y-axis, y component. So if I create that, you will see that the spring is gonna stretch all the way to 35 millimeter. That's a final length. So it's a 50 millimeter at the beginning, and it's gonna go to 35 millimeter is the maximum compression that it has, and that is gonna respond all of these plots and questions.